Hello everyone, this is group A20. We're going to teach you today about the composition of functions, f of gx. So, what is a composition of functions? Well, for the definition, let's suppose we have a function f that maps b onto c, and another function g that maps A on to B. Then the composition of f of g, which is written as f little circle g of x, or f inside of parentheses g of x, maps A onto C. So now we got this image that will illustrate an example of composition of functions. So let's say we got this first domain A, and within it we got some elements. We'll make them letters: A, B, H, Z. Then we got this codomain B, and we'll put some elements in there that are numbers, such as 1, 3, 5, and 9. And let's say there's some function between these two, G, that maps A onto an element, or maps these letters that are within A onto numbers that are within B. And it doesn't matter which one they map them to. At B go to 1, A go to 3, H go to 9, and Z go to 5. Now, let's say that there is this other domain, C, that has elements, doesn't matter what they are, we'll call them numbers, such as 10, 11, 12, 13. And there exists another function, F, that maps elements of B into this domain C. 1 goes to 13, 3 goes to 10, 5 goes to 11, and 9 goes to 12. So you can see G maps A onto B, F maps B onto C. So the composition of f of G is just a function that would map A all the way on to C. F of G of x is this function. For example, f of g of x of A would first go from 1 to 3 because of the g. A would go from A to 1, and then 1 would be mapped by the f function from 1 to 13 down here. Now we're going to do some examples that involve real functions. So let's say we want to compute g of f, and where the function g is defined from the domain of reals to the codomain of reals, where f of x is defined as x squared. And then g is the function from reals to reals, where g of x is described by x cubed. So then the function g of f of x will equal g of x squared, which would equal x squared cubed, which we all know equals x to the 6. So now a real example, using a value as an example. So g of f of x, of f of 2, it's going to equal g of 2 squared, which we all know is 4, and then 4 cubed is 64, which is just equal to 2 to the 6th power. So now another example is, let's once again compute g of f, but this time let's have these functions where f is the function that maps all unique names to the person's names, and then g is the function that will map all people's names to their initials. So then the function g of f of x will just be the function that maps all unique names to someone's initials. So then let's use my unique name for an example. So g of f of Murdoch W would be g of William Murdoch, because f will map a unique name to my name, which would then equal WM, because those are my initials, and G maps a name to initials. So then you can see the function G of f of x takes a unique name and maps it to someone's initials. So a property of compositions are that they exhibit the associative property. And as we all know from our basic addition and multiplication and subtraction, basic mathematics, that means that f of g of h of x will equal f of g of h of x, which will equal f of g of h of x. So as an example, let's say we have these three functions that map real to real. So let's say f of x equals x, and then g of x equals x squared, and then h of x will equal x minus 1. So then f of g of x is just x squared, and that means that f of g of h of x is just going to be equal to x minus 1 parentheses squared. Well, now g of h of x is equal to x minus 1 squared. So then it follows that this is equal to the f of g of h of x, because f of x is just equal to x. And then for the last condition, f of g of h of x, which is just x minus 1, is equal to f of x minus 1 squared, which is once again just equal to x minus 1 squared. So they're all equivalent, like the associative property says. So now, however, you must note that compositions are not commutative, and as we also know from simple mathematics, that means that f of g does not equal g of f. So as an example, let's consider once again two functions that map from real to real, where f of x is equal to x minus 1 squared, and g of x is equal to 3x. So then f g of x is equal to 3x minus 1 squared, and then g of f of x is equal to 3 times the quantity x minus 1 squared. And as you can see, these are not equal to each other. So just remember, it's not commutative. Another thing you guys should know about compositions is about compositions with inverse functions. So if you take two functions, f and f inverse, the composition of f inverse of x will equal x, and the composition of f inverse of f of x will equal x for all x. Now, for an example of this, let's consider two functions that map from real to real, where f of x is defined as 2x minus 1, and f inverse of x is defined as x plus 1 divided by 2. Now, from basic algebra, you guys can all easily see that these are actually inverses of each other. So let's look at the compositions now. F of f inverse of x will equal 2 times x plus 1, that's an x, divided by 2 minus 1, which, doing the basic algebra there, we see that comes out as x. Now let's do the other way. F inverse of x, f inverse of f of x will equal 2x minus 1 plus 1 divided by 2. And as we can easily see with our algebra, that is also equal to x. So one last thing that you guys should note about compositions of functions is the compositions of functions of itself. As you know, we can take compositions f of g, g of h. Well, we can also do f of x. We'll leave that to you guys to figure that all out for yourself, but as a simple example, assume that f is a function that maps from real to real that is defined as x squared. So then f of x is just going to be x squared squared, which would be x to the 4th. Alright, that wraps everything up about composition of functions. I hope you guys learned something today and continue coming and watching our podcast. Thank you.